Let's take let's take a look at two examples of the limit comparison test. First up, we have the series 3n plus 4 divided by 2n plus 1 quantity cubed. And our question is, does it converge or diverge? Now, to use the limit comparison test, you need to basically rule out what doesn't matter as n gets big. The plus 4 doesn't matter as n gets big. The plus 1 doesn't matter as n gets big. There's no need to carry forth these coefficients that are on the highest power here. And so for the numerator, we take an n. Now technically for the denominator, we can't just take an n. The entire denominator is cubed, so we take an n cubed. We don't need to carry forth the 2. So that's how you go out and choose another series called Bn. What does the series on Bn do? It's 1 over n squared. It's a convergent P series. As soon as you go out and get your B sub n, find out what it does. You must know whether it converges or diverges. Okay, so let's divide these two. Let's take the givens terms and divide them by 1 over n squared. Essentially, that accomplishes multiplying the numerator by n squared. So we end up with 3n cubed plus 4n squared. Denominator is 2n plus 1 quantity cubed. Ultimately, we don't have to multiply this out. Just be careful with the numerator. With the denominator. And what we end up with is focusing our attention on the leading terms. In the numerator, it's 3n cubed. In the denominator, it might look like 2n cubed, but don't forget you must square the 2 as well. If you have to, go ahead and multiply this out. Okay? But the leading term is going to be 8n cubed. They're both degree 3 polynomials. Whenever you have degree 3 or matching degree polynomials and you're looking for the limit of that rational function, you focus your attention on their coefficients, and it's the ratio of those coefficients. The answer to this limit is 3/8. Degree of the numerator is equal to the degree of the denominator. So we focus our attention on the coefficients on those leading terms, and it actually is an 8 as the coefficient in the denominator term. If you need to, go ahead and cube out 2n plus 1. But the cubic term will be 2n quantity cubed, which is 8n cubed. And so we have 3n squared and 8n cubed. The answer to that limit is 3/8. What does this mean? What you have is a finite constant. According to the limit comparison test, it says that the two series then will behave alike. You went out and got a convergent P series, so this given series will also converge. That's the first example. And next we'll have an example that's more difficult algebraically. We have 1 plus 3 to the n all over 4 plus 2 to the n. Start this at 1 and go to infinity. And our question is, once again, converge or diverge? That's the question. What do? You go out and get another series by disregarding terms that don't matter as n gets big. Disregard the plus 1, disregard the plus 4, and what you end up with is 3 to the n over 2 to the n. Alright, we need to be sure we know what this series does. The series then can be written as 3/2 the entire thing to the n. when you throw that inside the summation. What you have to recognize is that it's geometric. It's some ratio raised to the nth power. Every time you're going to get a term, it'll be from the previous term another power of 3/2. Why is it a divergent geometric series? You can tell whether a geometric series is divergent or convergent based on the value of the ratio. Here the ratio is 3/2, which is greater than 1, so divergent. You went out and get somebody who diverged, the inequality won't work, so you go for the limit. This isn't an easy limit to get to, though. A fraction divided by a fraction, we'll take the numerator fraction and multiply it by the reciprocal of the denominator fraction. Now we have to get sort of clever with our algebra. If we were just to distribute, there wouldn't be anything wrong with that. And what it does then, it gives us 2 to the n plus 6 to the n. If these guys are both to the n power, we can multiply them first and then raise to the nth. And that's how we get 6 to the n for these two parts here. Numerator and denominator. Alright, what do you try to do? Try to find this limit. And when you get stuck, appeal to the idea of focusing on the leading term in the denominator. In this case, it's kind of strange, but it's 6 to the n. And you multiply by its reciprocal. That's the technique. So what happens then? Distribute that across. 2 to the n over 6 to the n. Plus 1. 4 times 3 to the n over 6 to the n. Plus 1. The 2 to the n over 3 to the n, 6 to the n, can be put together as 2/6 all raised to the n, and that's how we end up with 1/3 to the n. Similarly, we're going to have 3 to the n over 6 to the n, and so we're going to end up with 1/2 to the n. And 3 to the n over 6 to the n is 3/6 to the n, which is half to the n. Just sort of fixing these up algebraically. The algebra is intense in this problem. Alright, great. Why do we do this? Well, we can know the convergence or divergence based on the value of this limit. If you have some ratio that is less than 1 in absolute value, then as n gets large, it's going to decrease down to 0. So we're left with the plus 1 from the numerator, plus 1 from the denominator. We end up with 1 as our limit. The limit doesn't have to always be 1. It's just the fact that it's a finite constant. And according to the limit comparison test, if you end up with a finite constant, then the two series will behave alike. Your series diverged, so the given series also diverges. And that's 2 examples of the limit comparison test.